So in the last video we talked about the names of the three sides of a right triangle and how to name those three sides based on what our angle of focus is. So make sure you're really good with that stuff before watching this video, because this video is going to get pretty intense. We're going to get into the real concepts of trigonometry, the stuff that you're going to be using as an engineering student all the time. So first, we start with the idea that an angle creates the side that is opposite of it. See how because of the wideness of this angle, it sort of extends into these two sides and opens up into this opposite side. So an angle creates the side opposite of it. And we can see here that this angle is decently big, so its opposite side is pretty big. But I can use a much smaller angle to draw a right triangle as well. And look at how this much smaller angle creates a much smaller opposite side. So we have the idea that an angle creates the side opposite of it. As that angle gets bigger, that opposite side gets bigger. And as you make that angle smaller, the side opposite of it becomes smaller. So this idea is a big part of this lesson here. So hundreds of years ago, there was a guy named Pythagoras who noticed this observation as well. And he was a mathematician, and what mathematicians did back then was that they studied shapes, and they looked for patterns in these shapes. And Pythagoras was the guy studying the right triangle. And like I said, he noticed this whole observation just like we did, but it wasn't quite the strongest pattern. And here's what I mean by that. Let's say that we had a right triangle with an angle of 75 that we were focusing on, and that 75-degree angle opened up to an opposite side of 9. Now this doesn't mean that all 75-degree angles open up to an opposite of 9. Check this one out. Here's a smaller right triangle, but it also has an angle of 75, but you can tell that this opposite side here is smaller than the 9. This one might be 5. So just because we have a 75-degree angle of focus doesn't mean it's going to be a 9 or a 5 or really anything. So just because the angle is big, like 75 is a decently big angle, doesn't mean that the opposite is going to be big. Like, because this is 9 and this is smaller, this is 5. So even though our observation that we looked at earlier was true, it's not the most solid pattern. But after a lot of experiments and drawing different right triangles and measuring sides and things like this, Pythagoras was able to discover a powerful pattern that made use of our observation. And here's what that was. An angle will produce a constant opposite over hypotenuse fraction. So let me show you an example of what this means. So here we drew a whole bunch of right triangles with an angle of 20 degrees. And notice how for each one of them, the opposite divided by the hypotenuse is 0.342. And remember, you can interpret fractions as sort of like percentages. Let's just say we had some random fraction, 7 divided by 25. My calculator says that's equal to 0.28. Another way of looking at that is that 7 is 28% of 25. So remember, fractions, decimals, are percentages. So what our whole 0.342 is saying is that our opposite is only 34.2% of our hypotenuse. And look at how that makes sense for each one of these triangles. Let's take the blue one. Look at how small this opposite is when you compare it to the hypotenuse of that blue triangle. I mean, it's kind of hard to tell that it's 34.2% exactly, but you can definitely tell that it is less than 50%. So what Pythagoras had discovered here was that the opposite divided by the hypotenuse for a 20-degree angle will always equal 0.342. And that's true no matter what. It doesn't matter how big the triangle is. Check our big green triangle here. It doesn't matter how small the right triangle is. Check our black right triangle here. It doesn't even matter if our right triangle is tilted and flipped over. The opposite divided by the hypotenuse of it will equal 0.342. So if someone told me the hypotenuse over here was 42, doing some quick math, I could figure out that the opposite side would have to be around 14.36. Because 14.36 divided by 42 gets me that 0.342 that I know that every 20-degree angle must have. So that's why Pythagoras had discovered that an angle will produce a constant opposite over hypotenuse fraction, because that fraction will be the same no matter what. No matter how big the triangle is, how small the triangle is, or if it's tilted at a wacky angle or something like that. So this right here was a very powerful pattern. And Pythagoras realized each angle, 30 degrees, 40 degrees, 70 degrees, etc., probably has its own special constant opposite over hypotenuse fraction. So Pythagoras performed a whole bunch more of these experiments here to figure out what those fractions were. And soon enough, Pythagoras had a list that looked something like this. And it should make sense to you why small angles like 5 and 10 have small decimals, small fractions. It goes back to our very first observation. This small angle will produce an opposite side that is a small percentage of our hypotenuse side. And vice versa for our big angles. Notice that they have big fractions, big opposite over hypotenuse fractions. And this is because those big angles will produce a relatively big opposite side when compared to the hypotenuse side. What these guys are saying here is that my opposite side will be 98.4% of my hypotenuse side. And for the 85, the opposite side will be 99.6% of the hypotenuse side. And also notice that these fractions, these decimals, will never be greater than 1. The reason for that is because our opposite side will never be greater than the hypotenuse side. The hypotenuse side of a right triangle is always the longest side. So because each one of these entries on the list was such a powerful idea, because they worked for any right triangle regardless of size and orientation, Pythagoras wanted to give this whole phenomenon he had discovered a name. And the name he chose to go with was sine. And it was taking a lot of time to always have to say, oh, the opposite over the hypotenuse of 5 degrees is always equal to 0.087. So what Pythagoras did was he said, okay, I'll just make it shorter. Instead of saying all this, I'll just say the sine of 5 degrees is equal to 0.087. And we pronounce it sine, but we spell it S-I-N. So all this word sine means is opposite over hypotenuse. This thing here means the exact same thing as this. This is just shorter. It's shorter to write and it's shorter to say. That's it. So after this, Pythagoras now had a much more concise, more organized looking list. And this entire sine list is in your calculator. You can calculate the sine fraction of any angle that you want. So now we're actually able to solve some right triangle problems with this new sine concept. Okay, so let's say we were asked to find the length of this side right here. Alright, so the 60-degree angles, let's focus on that one. We'll choose it as our angle of focus. I always start with my sides. This is hypotenuse, this is opposite, this is adjacent. And now because we know the hypotenuse's length, and they're asking for the length of the opposite, we can just use our new sine concept, because sine just means opposite over hypotenuse. So we can figure out that special opposite over hypotenuse fraction of our 60-degree angle of focus by typing sine of 60 into our calculator, which is 0.866. And of course we know that sine just means the opposite side divided by the hypotenuse side, which we now know to be 0.866. The opposite side is an unknown, we don't know it. Hypotenuse is 8, so if we do the algebra, 8 times 0.866, we'll discover that the opposite side's length is 6.93. And that's how you do it. Now let's say the question had a part B. Find the length of this side right here, the adjacent side. Well, we couldn't do sine of 60 again. But what we could do is a bit of a trick. What we'll do is we'll shift our angle of focus. Let's choose to focus on this angle right here, which you can figure out by remembering that for any triangle, all the angles must add up to 180. So if I do 180 minus my 60 minus my 90, I'll get 30 degrees right here. So if we choose to make this our angle of focus now, that will change the names of some of our sides. Of course, the hypotenuse is the same, but now this side over here, which used to be our adjacent, is now our opposite, and this one over here is adjacent. Of course, we already know it to be 6.93. But now, since we want to know this side here, and this side is now our opposite, we can do sine of 30. So my calculator tells me that the opposite over the hypotenuse of a 30-degree angle is equal to 1/2, 0.5, and we can just crunch the math again. Opposite is unknown, hypotenuse is 8, 8 times 1/2 is 4, so now we know the length of that last unknown side. So that's how right triangle problems usually work. You're given an angle and a side, and you have to figure out the other two sides. So check the sine practice video if you want more practice using sine. But other than that, that's it for this video. And in the next video, we'll learn that the world of trigonometry isn't just constrained to sine. There are other special fractions between the other sides.